Good morning, chemistry friends, and welcome. Here we go. We're going to start our final unit of the year, and it's about acids, bases. And I'll tell you, acids, bases is one of the largest fields of chemistry, and simply because most every chemical can fall into one category or the other. What I want to start with is a little segue from our equilibrium unit. What you can see there is SpongeBob is having a little breathing trouble, and I'll explain why. Right there, as you see that equation there, where carbon dioxide and water mix to make carbonic acid, which breaks down into hydrogen ions and bicarbonate, that is a key equilibrium reaction going on in your body that gets into balance. It's tied to respiration because of the carbon dioxide. And it's also tied to your blood pH, where the hydrogen ions and the bicarbonate and the carbonic acid are flowing around. Anyhow, the point is this: most living organisms, including yourself, are really a big mass of different equilibrium reactions, all trying to stay in balance with, breathing and the nutrition you bring in, et cetera, et cetera. One of the narrowest ranges that you can have, as you can see, there's your blood pH. Blood is normally slightly basic, slightly alkaline, and it doesn't have much of a movement that it can go either side without causing you issues, like with SpongeBob, a little hyperventilation. Right? So that's kind of the idea here to start with, is just showing you that equilibrium is a key component of living organisms staying alive, and chemistry is in there. Now, I put in a question: how will lowering carbon dioxide affect hydrogen? So if carbon dioxide levels drop and that is being removed out of its normal balance of the oxygen, carbon dioxide, respiratory exchange and stuff going on, and the cell respiration where the oxygen is being used up and the carbon dioxide is being created, etc. But that has a balance. If I remove this, how's that going to affect my hydrogen ion concentration over here? Well, if I remove that, all the equilibriums are going to shift left, because this will start breaking down more to replace the missing carbon dioxide. And these two will synthesize together to make that compound. So I'm removing the hydrogen ion concentration. So I'm getting more basic and more basic. And that can lead to a condition called alkalosis, which is not healthy. Right? So just a little biology, health, human being tie-in. All right. Here's the other thing we've got to talk about, and this is solution stuff. And acids and bases are no different, and it's about dissociation. Easy for me to say. You know that when we put things in water, a compound separates into its ions, an ionic compound, and even while polar compounds don't dissolve into ions, they do dissolve into smaller bits, or the molecules separate out. But anyhow, let's think ionic compounds. When a compound separates in ions in solution is dissociation. Even water dissociates. So there's always a balance in water where you have two water molecules. One of them is going to lose one of its hydrogens and give it to the other. This is called a hydronium ion. Okay. The easy way to write this is just water will separate into hydrogen and hydroxide. And that's constantly going on. Every molecule goes through it at some point, but there's a constant number. So it's constantly going on, but it's at equilibrium. So at any point, those concentrations are all the same, but all water at some point is losing a hydrogen, getting it back, separating the hydrogen and hydroxide and getting it back. Okay. Now, one of the things that makes water special is it's considered amphoteric, which means it's both an acid and a base, as we're going to define. Why is it both an acid and a base? Because when it dissociates into water, it gives a hydrogen ion, which is the key for an acid, and it gives a hydroxide anion, which is the key to a base. Okay, so Here we go, just some background, and you can see what we just did here, and this is the same if I mix anything in water, okay? Like this hydrochloric acid, I mix it in water, it's gonna lose the hydrogen. It's gonna give it to make that hydronium ion, okay? And it's gonna have the chlorine out here. But that just means it's an acidic solution because it donates that H to the solution. It separates into H and Cl, and then you get H and Cl minus. You could write this just as H plus. It'd mean the same thing. Some properties: acids ionize in water to produce hydrogen ions. They taste sour. They react with metals, certain metals, to kick out gas, as we saw in the gas labs. They react with carbonates to make carbon dioxide. They conduct electricity. Bases, on the other hand, when they ionize in water, produce hydroxide ions. They taste bitter, they feel slippery, and part of the reason they feel slippery is bases are very good at dissolving oils, so they dissolve that protective oil covering on your fingers. So that slippery isn't the soap or whatever you feel on it, it's the fact that you remove the oil and you're kind of feeling the actual skin-on-skin feel. And they also conduct, both acids and bases are electrolytes or electrolytic solutions. They can conduct electricity, okay? There's some common household acids and bases. You can see right there, lemon juice, baking powder, stuff like that. Here's baking soda, a lot of cleaners, a lot of cleansers. We talked about an equilibrium ammonia as a big base in a lot of these things because it provides that. It's one of the most chemically produced compounds because it is the basis for a lot of these bases. That was nice. And here, just a little roll of the pH scale where you can kind of see where things land. Stomach acid and fruits with citric acid in them, and more soaps and bleach and bases and stuff right here. Okay. All right. So we have three definitions of acid base, of which the first two are really only important, and we're going to talk about those today and then do something else next week. The first and earliest was Arrhenius, who, if you just think of naming, said two simple things, which we'll look at in more detail in a minute. Acids start with H, bases end in OH. Okay? And if you think back to your naming from two terms ago on our acid base page, acids started with hydrogen, bases ended with hydroxide. Okay. That was the first. We're going to talk about that in a minute. That was the first, that was the earliest, that was a defining thing. But then other definitions and supplements had to come along because there are things that are acidic that don't start with hydrogen. There are things that are basic that don't start with or end in hydroxide. And so the second one we see often, and it's common because ammonia is the big one in here, is Bronsted-Lowry changed it. Instead of saying, okay, technically with Arrhenius, acids increase the hydrogen concentration in solution when I throw an acid in, and bases increase the hydroxide ion concentration. It focused just on the hydrogen. So the Bronsted-Lowry theory about things, when you're adding things to water, really talks about the hydrogen in it. And so while the hydrogen doesn't really change, Arrhenius acids and Bronsted-Lowry acids are all the same thing, as you can see by our examples. It just changes to say that acids give a hydrogen ion. But what it changes to bases is bases accept a hydrogen ion. So it includes anything that's a base, or most anything basic that's not ending in OH. So it includes ammonia, which doesn't have an OH in it, but is a very strong base and one of the top 5 chemicals made in the world. And then after that, and we're not going to talk about this one, but it does also allow for solids and gases and other nonmetal ions or metal and nonmetal ions. That Lewis acids and bases, it talks about the acid accepts, is an electron acceptor to make a new bond, and a base is an electron donor. Don't worry about that much. I put it in there just to tell you that, as I said in the beginning, most everything can be categorized as an acid and base. because they function as acids and bases. But you had to find different ways to, this works with things that do not have hydrogen as an acid. Okay, but work as acids even though they don't have a hydrogen. So the idea that we have 3 different types of naming isn't so much that they're different types, is that they're starting to cover other things that don't fit the initial Arrhenius definition. Okay, anyhow, let's go back to Arrhenius about 1884. Proposed it did, there's some nice typing, proposed it did that acids are substances that release hydrogen ions into water. So for that example there's a hydrogen dissociating into hydrogen and chlorine. And I gave you a couple of old questions that you can think about in your head of whether the hydrogen ion is a cation or an anion. And when I'm writing equations, what does AQ mean? Anyhow, that was a basic thing. And the easy way to say it is all acids start with H. Okay. Here was the base proposal. Proposed, type better this time, the bases are substances that release hydroxide ions. So again, you see the dissociation of sodium hydroxide when you make a solution of water. And it gives you the sodium ion and the hydroxide ion, and this is the key to a base. So that was Arrhenius basically saying acids start with H, bases end in OH, there you go. Okay. So let's look at Bronsted-Lowry. Bronsted-Lowry then had to explain, kind of talked about weak acids and bases, and we'll talk about what's the difference between a weak acid and a strong acid, weak base, and a strong base later. But it really does, again, as I said before, account for bases without hydroxide. Things that act like a base but don't have hydroxide in them, like ammonia. Bronsted-Lowry acids are proton donors. Proton is just, if you see a hydrogen, H plus and proton are the same thing, because a hydrogen ion has lost its electron. That's why it has a +1 charge. It has no nucleus. Sorry. If you think of a hydrogen atom, it has 1 electron, 1 proton, 0 neutrons. So when it ionizes by getting rid of its electron, then it only has 1 proton. That's the only thing in the nucleus. There's no neutrons, so it's called the proton. Hydrogen ions are called the proton in chemistry. So Bronsted-Lowry acid says that it's the acids that give the H. Donate the H plus, the proton. A Bronsted-Lowry base then is the thing that accepts that hydrogen ion. And that's why it's called a proton acceptor. Again, proton and hydrogen ion are terms that are similar. With any of those, then you have what's called a conjugate acid or a conjugate base. And all that is what's the product? Okay. So when a compound gives up its H plus, whatever's left over from that compound is the conjugate base. The conjugate acid is what's there when the base has taken on that proton. So, and I'll show you what that means. And you can think of it this way: base accept, acids donate. Okay. It's bad. Sorry. So here was my Bronsted-Lowry base. Here was my Bronsted-Lowry acid. It was just the water. Okay. The acid gets rid of the hydrogen. Okay. So it's the donor. The base accepts the hydrogen. So it's the acceptor. That's why it's the base. Here's the conjugate acid of the base is what was ammonia, the ammonium ion. That's what happened when it took the H. It became ammonium. So this is the base. This is its conjugate acid. This was our acid. The hydroxide that left over is what's called a conjugate base. Okay. You don't have to get that right away. This is all defining stuff. Just wanted to get it out there. This is the start of our unit. Now, tomorrow, Friday, is just cleanup day. We're not going to have any assignment. We're not going to have anything else. It is cleanup day. It is getting in old labs that is doing so. It's just get your grade cleaned up to where it is, get yourself a breather, catch up, maybe feel free to watch this again if need be, maybe go back and review how to name acids and bases at some point. Don't care. It's a chemistry lightning target day, whatever. It's a cleanup work day. Anyhow, there we go. That's enough for today. Enjoy the day, relax a little bit. We'll be back at it tomorrow, just giving you a quick video on how to relax. Talk to you later.